Hi everyone, welcome to Vidhyalakshmi School YouTube channel. This is Naresh Reddy, Chemistry faculty of Vidhyalakshmi CBSE School. Okay, now let us discuss about one of the most important topic of J and NET. Our topic is colligative properties of +2 solution chapter. Okay, so here in this session, what we are going to discuss means what are colligative properties, how many properties are there, those properties depends on what and independent on what, okay, and those properties are they related to the molar mass of solute or not. So those concepts let us discuss in this session. Okay, so shall we start? Yes, let us go to last colligative property, that is osmotic pressure. If you see this diagram carefully, okay, so here I am filling, that is I am taking a flask, I am keeping a semi-permeable membrane at middle of this flask. That semi-permeable membrane allows only the solvent particles but not solute particles. After that, I am separating this flask through semi-permeable membrane, okay. After separating, I am filling in one half with a pure solvent, and in another half I am filling with solution like this. So solution means solute and solvent both are present, means green and blue, but pure solvent means only one kind of particles there, that's why only blue. So if you are seeing after some time, some blue colors are enter into this solution side, so that solution level increase. Okay, why that is happening here means this membrane allows only the solvent molecules. Okay, in pure state more number of solvent molecules there, but in solution state less number of solvent molecules present. Okay, always a solvent flow from more to less. So since here more number of solvent particles present, here less number of solvent molecules present, solvent molecules are moving from the pure solvent to solution, so that solution volume increases here. Okay, that process of moving of the solvent molecules from the pure solvent to the solution or from dilute solution to the concentrated solution we are calling as osmosis. We have to write down on this solution side as pi plus atmospheric pressure. Some atmospheric pressure applied on the surface of this solution, that won't stop the passing of solvent molecules into the solution. Okay, we have to apply excess pressure, so that atmospheric pressure plus our pressure both are applying on the solution. Okay, but if you are applying excess pressure on the solution, then passage of the solvent molecules from the pure solvent to the solution prevented. That excess pressure we are calling as osmotic pressure. That osmotic pressure we are representing with pi symbol. Okay, here how much pressure we have to apply to stop the solvent molecules from the pure solvent to the solution, that pressure we are calling as pi. If you are applying than that required pressure, okay, if you apply than that required pressure, then now solvent molecules move from solution to the pure solvent. Okay, this movement from pure solvent to solution we are calling osmosis. Okay, if we apply excess pressure than required for the osmotic pressure, then now solvent molecules move from solution to the pure solvent. That process we are calling a reverse osmosis, because it is reverse of osmosis process. So that is called a reverse osmosis. Okay, so if you are applying the pressure below the atmospheric pressure of a solution, then osmosis process takes place. If you apply a pressure above the osmotic pressure on the solution, then a reverse osmosis process takes place. If you apply the pressure which is exactly equal to the atmospheric pressure of that solution, then osmosis and reverse osmosis not takes place. Okay, then both the volumes in the flask is same. How much initially we took? That same volume present. Okay, if you apply the pressure less than osmotic pressure, then solution volume increase, solvent volume decreases. If you apply the pressure excess than the osmotic pressure on the solution, then solution volume decrease, solvent volume increase. Is it clear? Right. So this is about what is osmosis and osmotic pressure, and what is the role of semi-permeable membrane here. Is it allow only the solvent molecules, or is it allow the solute particles also? Means allows only solvent molecules but not solute particles. Okay. Now for dilute solution, if we take that osmotic pressure we are representing with pi. So if we take for dilute solution, for any dilute solution, pi is directly proportional to temperature and pi is directly proportional to molarity. Okay. Here m is nothing but molarity. In depression in freezing point and elevation in boiling point, those two are directly proportional to molality, but osmotic pressure is directly proportional to molarity. Okay. So if we combine collectively this, that molarity term we can also represent as concentration term C, that is concentration. Okay. C is nothing but number of moles present in 1 liter volume, nothing but molarity. Number of moles present in 1 liter volume of solution is called molarity. So that m we are representing as C. Okay. So that C formula I am writing here. So that pi is directly proportional to n by v into T. If we remove the proportionality, then we can get a proportionality constant R. Okay. That is n by v into RT. So number of moles is nothing but weight by molecular weight. So if we substitute that, then we can get overall like this. Okay. Here V is in ml. Here V is liter, but here we are converting that one to the milliliter, so that 1000 come. So this is the final equation to calculate molarity of, that is osmotic pressure of that solution if amount of the solute is given. Okay. If number of moles of the solute is given, then this is the equation to calculate osmotic pressure. If concentration is given directly, then we can calculate as like this, pi equal to CRT. That is this equation. If concentration is given in molarity, capital M. Okay. So in this, if we see up carefully, here weight W is nothing but weight of the solute and M is nothing but molecular weight of solute. So is this molecular weight of solute inverse or directly proportional to the osmotic pressure? Means inversely proportional. So that we can say this molecular weight of solute is inversely proportional to the osmotic pressure, which is one of the colligative properties. So here relative lowering of vapor pressure, it is inversely proportional to molar mass of solute, and elevation in boiling point, that is also inversely proportional to molar mass. Depression in freezing point, that is also inversely proportional to molar mass, and osmotic pressure also inversely proportional to molar mass. So that every colligative property is inversely proportional to molar mass. Okay. And here what is I means, that colligative property is also depends on want of factor, that is I. Here I we are calling as want of factor. Want of factor. Okay. So how do we calculate that want of factor? Means I is equal to number of particles after dissociation or association by number of particles before dissociation. Number of particles before dissociation or association. For example, KCl I am taking. KCl. Okay. Before dissociation I am taking this one as one particle. But after dissociation it dissociates to K plus and Cl minus. Okay. So that it gives final value how much? 2. So after dissociation particles 2. Before dissociation 1. So that what is the value of I for this means 2 by 1, that equal to 2. Okay. So here all these colligative properties are directly proportional to I. So that we can say any colligative property is directly proportional to I. Okay. If I value increases, then colligative property is more for that. That type of concepts we will discuss in problems. Okay. So here if we include the want of factor I, then only we can get exact value of colligative properties, and it is coincide with the theoretical as well as experimental value. Okay. Is it clear? Right. So this is about want of factor and how do we calculate that I value, and if we include the I value here, then what are the equations of colligative properties? Okay. These equations we have to take during the problem calculation part. Okay. Right. Now let us see what are isotonic solution, hypotonic solution and hypertonic solution. If I am taking two solutions, if those two solutions show the same osmotic pressure, then we are calling those as isotonic solution. Okay. To say two solutions as isotonic solutions, then osmotic pressure of one solution should equal to the osmotic pressure of another solution, means pi 1 is equal to pi 2. Since we can write down as pi 1 equal to C1 into RT and pi 2 equal to C2 into RT. This is for first solution, this is for second solution, and he is saying those two solutions should have the same osmotic pressure at all temperatures, means at same temperature they should show same osmotic pressure. Since temperature is same or value same, then we can omit those. Then if pi 1 is equal to pi 2, then C1 RT equal to C2 RT. Since temperature or value same, those two cancel, so that we can get C1 equal to C2. That's why to say two solutions as isotonic solutions, to equalize the osmotic pressure of those two solutions as same, we have to prepare those two solutions with the same concentration. Then only those two solutions are isotonic solution. This is the condition to prepare isotonic solutions. Those two solutions concentration should be same. Okay. So here what is the example of isotonic solution means? Blood is isotonic with 0.9% m by v saline water. Saline water means NaCl in water. Okay. That saline water is nothing but NaCl in water, means aqueous sodium chloride, with how much concentration? 0.9% m by v, means 0.9 gram NaCl in 100 ml water. That is called 0.9% m by v saline water. Okay. This concentration, if we prepare NaCl in water, then that solution shows how much pressure, osmotic pressure. That same osmotic pressure is shown by our blood. Then only we can inject that saline water into our body. If we prepare the saline water concentration less than this, that is 0.9%. If we prepare less than 0.9% m by v solution of NaCl or saline water, then that less than 0.9% m by v solution acts as hypotonic solution. Which one show less osmotic pressure than blood. Okay. If we prepare greater than 0.9% m by v NaCl solution, then this one behave as hypertonic solution. Hypertonic solution means this solution has more osmotic pressure than our blood osmotic pressure. Okay. But this one is behaving as hypotonic solution, means this solution show less osmotic pressure than our blood osmotic pressure. Okay. So hypertonic solution means that solution osmotic pressure should be more or less? More. To say hypotonic, that solution osmotic pressure should be less. Okay, if both solutions are osmotic pressure same, then isotonic. So blood is isotonic with what percentage of NaCl only means 0.9% m by v. If it is greater than 0.9%, then acts as that saline water hypertonic solution. If it is less than 0.9%, then that saline water acts as hypotonic solution. Okay, so let us see here again those definitions. The solution which has less osmotic pressure is called hypotonic, and the solution which has more osmotic pressure is called hypertonic solution. So examples also given here. Less than 0.9% m by v, saline water is hypotonic solution. If we inject that saline water into our body, then since our blood pressure is, that is blood osmotic pressure is more, this solution osmotic pressure is less, then blood cells swell. Blood cells swell means the water molecules, nothing but solvent. Those water molecules when enter into our body through this saline water, then inside of into the blood cells water enter, so that blood cells swell. Okay, if you are taking the saline water greater than 0.9% m by v solution, then that solution acts as hypertonic, so that water is coming from the cells to the outside, so that blood cells shrinks. Okay, so if any of these two solutions if you are injecting into our body, then blood cell swells or blood cell shrinks, then a problem arises to us. That's why we always take this saline water with how much concentration means 0.9% m by v. Then only our blood is showing the isotonic with saline water, so that our blood pressure go as usual. Means blood circulation go as usual. Okay, so this is about colligative properties. Okay, and the relation between colligative properties to the molar mass and want of factor. Okay, right. So thank you for watching this video. Okay, so in this session we discussed about what are colligative properties and how we will measure the colligative properties of those, and what is the relation of those colligative properties to the want of factor and molar mass of the solute. Like this video. Okay, so if you like this video, please share, subscribe and share to your friends, so that I will try to upload more videos. Okay, and in next video let us see with another concept. Okay, see all of you in next video.